this lesson, I'm going to introduce you to one of the most important ideas in all of mathematics, and that's the idea of a set. Now, in the simplest terms that I can possibly give you, a set is really just a collection of stuff. So for example, I want you to imagine that we had a set of pool balls. Now for this set of pool balls, the set is the actual group that contains all of the individual balls, and each element is each individual pool ball that goes inside this set. Now this diagram that I've drawn here is usually called a Venn diagram, and it doesn't really matter where you place each individual ball. The only thing that does matter is whether or not the ball is inside the set or outside the set. Usually, we denote sets with a capital letter. So for example, let's imagine that we call this set S. Now it is always possible to draw each element inside a Venn diagram, but there is actually another way that we can write down sets too. So let me go ahead and show you what that way is. Now down here, I've gone ahead and just copied all of the individual balls that appeared in the original set. Now usually to write this set, we can also write it with a curly brace separating each element with commas, as I'll show you now. So these two representations of sets are exactly the same. You can either draw the set and each of its elements in a Venn diagram, or you can also just go ahead and write it in between curly braces. These braces over here are the curly braces. Now, because a set is just meant to contain a bunch of elements, the order in which we place these elements into the set does not matter at all. So, for example, we could go ahead and swap this 7 and this 9, and we would still have the exact same set. Now sets actually serve almost as the foundation of all of modern mathematics. They are useful for many things, but one of the simplest things is to just count. So for example, we have a number of pool balls in this set, and if you were to count them all one by one, you'd see that you have 4, 8, 12, and then 15. The number of elements inside of a set is called the set's cardinality. We usually denote the cardinality of a set with these vertical bars over here, and the cardinality of this set S over here is actually equal to 15. However, not every single set out there has a fixed size like this. There are many sets out there that are actually infinitely sized sets. So if you had a set that was infinitely large, we'd use this symbol over here, the infinity symbol, to denote its cardinality. Now, without really looking at more than just this set, I can't really give you a good intuition for how sets work. So what I'm going to do first is I'm going to look at a whole bunch of different sets, and we can, together, decide whether they're finite or infinite. Now, the first set I'm going to talk to you about is the set of bird species. I want you to think about every species of bird that has ever lived on this planet. Now in this set, I've drawn just a few different birds that do belong to this set, and I've labeled this set capital B. Now it's more or less impossible for me to draw every bird that ever existed here, because A, there are way too many of them, and B, I haven't even seen every single bird that's ever existed. Now every dot that I've added to this diagram here represents another species of bird that should appear in this diagram. Now, if you think about this set, just for a moment, I think you'll come to understand that it isn't actually an infinite set. If you think about it, the number of birds that have ever existed is finite. It's very large, the number is huge, but it is finite. So aside from the set of birds, there are many other sets out there. So for example, I want you to imagine a set of photographs. I want you to imagine that this set of photographs here contains 4 photographs that you took on your last vacation. In fact, it contains your favorite 4 photographs. Now, because this set only contains 4 things, we would say that the cardinality of this set is just 4. Now, I'm going to show you another idea that's also a little bit strange, but it's also quite important when you're thinking about sets. I could arrange these 4 photographs into a single set. Now, this stack of photographs here represents the exact same set that you had over here. But then it's also possible to have a set that contains multiple photograph sets. So for example, you could have a set of photograph sets. Now therefore, this set A over here, the photo album set, contains a set of photo sets. So you have 1, 2, 3 photo sets. Now, despite the fact that we have a bunch of photographs in each of these sets, we're going to say that this set contains a bunch of photo sets. And because it only contains 3 photo sets, the cardinality of A is just 3. Now at this point, you're probably waiting for me to give you an example of an infinite set. We have a few different sets here, but they're all finite. Now, I want you to think about this set this time. Now, in this set, I've drawn a lonely triangle. I want you to imagine the set that contains every possible triangle that you could ever draw. Now, if you imagine every possible triangle that could ever exist, then we actually come to a very interesting point. Unlike the set of birds over here, the number isn't just large, but it's technically infinite. Unlike the set of birds, if you took a particular triangle, you could just take that triangle and then say double its size, or you could triple its size, or you could multiply its size by 1.2. You can make really thin and narrow triangles. You can make triangles that have 2 sides that are approximately the same. Or you could just keep going for as long as you like, and you'd never run out of new triangles to put into the set over here. So therefore, we can say that the set of all possible triangles is actually an infinite set. But there is actually one more infinite set that's actually much more obvious than the set of triangles. And that's just the set of all numbers. Now in this set, I've just written a whole bunch of numbers, some of which you may have heard of and some of which you may not have heard of. So we've got the number 5 here, the number -7. We've got this one called pi, and then we've got 100 and √2. But here's a funny thought. No matter how long you spend adding numbers to this set over here, you will never run out of new numbers to add to this set. And therefore, because you're never actually going to run out of new numbers, we can say that the set of numbers is actually an infinite set. Now, just in case you weren't totally in agreement with me when we talked about the number of triangles being infinite, I want you to understand that you could always make a triangle with any number as one of its side lengths, and therefore, you aren't actually ever going to run out of triangles to make either. Now, by just looking at these sets over here, I hope you can come to the appreciation that sets are actually a very general mathematical object. And I would go so far as to say that sets are useful because of how simple they are. But now that you've actually seen a few sets yourself, I think it's a good time to actually continue talking about some of the conventions we use when dealing with sets. Now, it's possible to write a set like this with a Venn diagram, or with curly braces and then writing the elements explicitly. But there are also other ways that we can do it as well. Now, aside from writing the set explicitly, we can also construct sets with a rule. So for example, we could use the rule that the set W contains all of the warm, solid colored balls. Now, despite the fact that you can always construct a set with a sentence, sometimes sentences can actually cause you to miss or to add extra balls that you may not intend to be in the set. However, for this rule, we're interested in the warm, solid colored balls, which you can see is this number 1, this number 5, and this number 3 over here. Now, aside from using rules, we can also use patterns to help us build up a set. So for example, it is possible to build a set that contains all of the balls that have an odd number printed on them. Now, you probably noticed that I swapped the 3 and the 5 while I was making this set. Now, despite the fact that I said that order doesn't matter, if you're going to actually use a pattern to build the set, you better hope that you have the order in a way that somebody can understand. By their very nature, patterns have an order. So for example, you start with 1, then you jump to 3, and then to 5. If you have this in a different order, it wouldn't be very clear that you're talking about the odd numbers. Now, patterns are actually a little bit problematic when you're building sets, because it is possible to have more than one possible set that follows this pattern over here. So, for example, you could start at 1, jump to 3, go to 5, and then go to 12 if you wanted to. Now, the whole point of this is that this ellipsis hides a few of the elements, so we don't have to explicitly write them out. But you need to be careful because they can mean a whole bunch of different things. So therefore, despite the fact that using an ellipsis to build up a set is actually a little bit problematic sometimes, we still allow it because of the amount of convenience it provides us when we build up a set this way. But generally speaking, if the set you're trying to build is any more complicated than this set over here, you should probably think twice before using an ellipsis like this. Now it turns out that from simple sets, we can actually construct more complicated sets, and that's one of the main reasons why sets are so useful. However, there are also some special sets that you should know about. Now, before I leave you for today, I want to show you a few simple examples of how we can actually construct sets like this. So let's work through some of these examples together. So to get us started, let's construct a set of odd numbers between 0 and 20. So that's one way to do it. We can just write the odd numbers between 0 and 20. But how about we try doing it with a pattern as well? So this time, we start at the number 1 and we go up by 2s. So we have 1, 3, 5, and then these ellipses indicate 7, 9, 11, and so on. However, the last element in this list is not actually the number 20, because 20 is actually an even number. So you need to take the number just before 20, which is the number 19. Now in this case, it's also possible to write the set out explicitly as well. But for some sets, especially infinite ones, it's not really possible to write out every possible element. So for example, let's consider the set of all positive even numbers this time. So this set E plus is, as we said, the set of positive even numbers. Again, you could leave it like that, but there are other ways to write it too. So using a pattern, we could start with a number 2, and then again go up by 2s. So in this case, we start with the number 2, and then we increase by 2s. So we've got 2, 4, 6, 8, etc. But then when we get to this etc., which we indicate with this ellipsis, where do we stop? Where do these numbers actually end? Well, you could prove very easily that there isn't actually a largest even number. Because if you took a huge even number, then you could always add 2 to it to get to another even number. And therefore, these don't actually end. And you just need to write a closing brace over here without writing the final elements. Now, this ellipsis, immediately followed by this curly brace, is actually a little bit of a problem for some mathematicians out there. The idea that you could never actually finish writing out all of the numbers, no matter how much time you were given, indicates that there's something a little bit strange going on with infinite sets, and you're going to see a little bit of that in future lessons. But now to show you one more example, I actually want to show you the set of all even numbers, including all the negative ones. Now, in the case that you actually wanted to write this with a pattern, it turns out that the numbers continue in both directions. Let's start with the even numbers we know. Now, you count up by adding 2 to the previous number. So you go 2, 4, and 6. And that means to count down, you have to subtract 2 from the previous number. So you get 6, 4, 2, and then below 2, you get the number 0. Now, if you just continued doing this, you'd actually again never run out of numbers in this direction either. So therefore, you can't just write an ellipsis at the end, but you also have to write the ellipsis on the left-hand side as well. So therefore, the way to construct the even numbers is to start off with some random even number, and then add 2 every single time as you go to the right, and then to subtract 2 every single time as you go to the left. And you have to continue this more or less forever. So I hope by now you've got a pretty good intuitive sense of what a set is. I think this just about completes the examples, so let's go ahead and summarize everything. In this lesson, we introduced the idea of a set. As we said, a set is just a collection of elements. So this whole thing is a set, and these things inside of it are the elements. Now it turns out that you can make sets out of basically any object you like. And in fact, as you study higher and higher levels of mathematics, you'll be making sets out of all sorts of crazy things, not just pool balls. Aside from being able to represent the set with a Venn diagram, You can also represent it with a capital letter, and you can also use a curly brace and write the elements explicitly. The size of a set is what we call its cardinality, and in this particular case, since there are 15 balls, we said that the cardinality was just 15. Now, other than constructing the set explicitly, as we did down here, we can also construct the set using either rules or patterns. A rule is usually just an English sentence, and a pattern is something that you can follow to easily figure out the missing elements that you didn't have to write down. There are some sets that are a little bit more important than most of the others, and we call those sets special sets. The simplest special set is the empty set, and it's just a set that contains absolutely nothing inside of it. So it's like a Venn diagram where you didn't put anything inside. Now, initially, when you first learn about them, sets seem pretty simple, and their importance won't immediately become clear to you. Only later, as you study more and more mathematics, will you start to see how incredibly useful these sets actually are. Now, immediately following this, we're going to try to establish the relationship between sets and the elements inside of them. And we're also going to try to figure out how you can actually use old sets to build up new sets in different ways to the ones that I've just shown you here. But aside from this, I'd like to say that this is the end of the lesson on introducing sets. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.